Hi everyone, and welcome to this partner webinar titled Accelerate Development and Optimize In-Field Device Quality with Remote Debugging and Monitoring. My name is Ali Aljani. I'm a developer marketing manager at Nordic Semiconductor. We are very excited to have with us today Chris Coleman, the CTO and co-founder of Memfault. As for the agenda of today's webinar, I'll start with a brief on our Cellular IoT offering and the latest additions to our NRF91 series. Then I'll hand it over to Chris, where he'll talk about what it takes to ship hardware, integrating device reliability engineering, getting started with Memfault plus Nordic in 5 minutes, and key metrics for battery and connectivity. Building a reliable cellular IoT product, whether it's LTM or narrowband IoT based, is complex. But here at Nordic, we make it simple and we enable our customers to get to market fast. Our goal is basically streamline the cellular IoT product development and support the entire product lifecycle for our customers. How do we do that? We do that by integrating the different parts of a cellular offering into a complete solution. So first of all, we have pre-certified best-in-class hardware and modem stacks. This is basically the NRF91 series. But we don't just give you great hardware, we give you with it a great software. That's the NRF Connect SDK with comprehensive set of samples and applications that covers all the corner cases and all the application protocols. So things like MTT, co-op, lightweight machine, HTTP, HTTPS, you name it, it's there. In addition to the great software development kit, we have extensive set of hardware and software development tools. So we have the Thingy 91. That's a great prototyping platform with a lot of sensors, and it has a great application, the asset tracker with interface to the cloud through our NRF cloud. And we also have the Power Profiler Kit 2. That's an actual affordable kit that can give you real-time power consumption. And when it comes to the software tools for development, we have the cellular tools, things like the cellular monitor, which is quite essential to give you insights into the network parameter and network performance. When it comes to support, we have world-class support. So for training, we have a dedicated free online course on our Dev Academy. The course is called Cellular IoT Fundamentals. So if you are new to cellular IoT technology, we highly recommend this online course for you. And when it comes to tech support, we have a team of expert engineers eager to help you. And here you can create either private or public tickets. And of course, we have extensive partner program, and that's why we have Memfault, because we acknowledge the complexity of a cellular IoT product, and we know you need to have a rich, complete solution, and we value very much our partnership with Memfault. They give great reliability and observability solution to our customers. So in addition to that, we also have NRF Cloud with great services, so things like location services, for example, that gives you very low power solutions for location, so it improves the power consumption for cell-based location and also Wi-Fi based location and GNSS based location, in addition to other services. So it's a complete solution that enables customers to get to market very fast. Let's talk more about the hardware, the NRF91 series, and before going there, let's just take a look at a traditional cellular IoT hardware design that does not use the NRF91 series. It would contain a host MCU, that could be basically anything, an RF front end, a cellular module, and then the host MCU will control the cellular module serially through 80 commands. And if locations is needed, you would add a GNSS module. And of course, in cellular IoT design, you would deal with a lot of certificates and credentials, and these, they must be stored securely. So you would need to add a secure element. And to power all of these components, you would need to have a sophisticated power management IC. So that's the old traditional way of doing things. At Nordic, we take all of these components and put them into one integrated package. That's the NRF91 series. We have 3 variants I'll cover next. And this is a new and a better way to design cellular IoT products. So on the left, we have the old traditional way of doing cellular IoT. That's the fragmented ownership. You have a module from a company, let's call this company B, and then they most probably have a modem, cellular modem from another company, and they develop their own closed firmware. And of course, for your design, you need to have an MCU and then manage this communication yourself. You need to add your own security element and own sophisticated PMIC to power the whole thing. So it's a complex design. It's a complex bit of material. We're dealing with supply chain issues. You're dealing with tech support from different vendors, different kind of like channels. So it's a lot of complexity just by the look at the design. If you take a look at the Nordic solution, where you have full solution ownership. So it's lower complexity. The application processor and the modem, it's in one package, and it's really integrated. In addition to the modem and the application processor, you have the security element. So for example, the nRF9160, that's a PSA certified level 2. You also have the GNSS module inside the package. You have the PMIC, passive, crystal, and RF front end. So it's a lower complexity design. And when it comes to power consumption, it's the lowest cellular IoT solution in the market. You have tools to verify that. So we have I mentioned the Power Profiler Kit 2 that give you real-time measurement. And in addition to the Power Profile Kit 2, there is also the static Power Profiler available on DevZone. You just put the parameters and the configurations, and they give you a static power measurement. Smaller size, really integrated solution. And the total lower cost, you're no longer dealing with different discrete component. It's just one system and package. So the total cost for your product will be less, and it's a simpler supply chain. Everything is integrated. When it comes to support and maintenance, it's way simplified. You're no longer dealing with different vendors. And also, I probably forgot to mention that the nRF91, for example, 9160 is globally certified, and there's a map coverage available on the website. Lastly, I would like to talk about the available variants in the nRF91 series. So we have the nRF9160 system and package. This was actually released in 2018. It has a mature and globally certified stack. This is the lowest power consumption cellular IoT solution in the market. It's also PSA level 2 certified. This year we announced two new variants, the nRF9161 system and package and the nRF9131 mini system and package. They are similar in some aspects, so they all incorporate an application processor, which is a Cortex M33 clocked at 64 megahertz. They all have a floating point unit, DSP instruction set, cache, 1 megabyte of flash, and 256 kilobyte of RAM. And of course, you have the security element and a rich set of peripherals. But when it comes to the differences between these variants, the 9160 supports 3GPP release 13, while on the 9161 and the 9131, this has been bumped up to release 14 with extra new features. And the 9161 and the 9131 support DECT NR Plus through the 1.9 gigahertz band. And this is ideal for 5G non-cellular mesh network. And you also see that it has a new development kit and a prototyping platform. Also for the 9131, there is a new evaluation kit. And you can see that the size of this is really integrated and small. So it's actually smaller than the previous kind of like variants. And this is done by taking the PMICs out. So it's ideal for size constrained designs. And with that, I will hand it over to Chris. Chris, could you please introduce yourself and take us through your slide? Thank you.
Thanks, Ellie. And hi, everyone. Excited to be here today. I'm Chris Coleman, co-founder and CTO at Memfault, where we build a reliability platform that helps folks like you remotely monitor devices in the field and debug problems that crop up. Prior to starting Memfault, I had spent my entire career in the embedded space. I worked on servers at Sun Microsystems and then found myself at a few different wearable companies like Pebble and Fitbit. Across the board, I was always the embedded engineer who got a bit too excited about strange problems in the field. So support tickets like, why did the battery die in 1 day instead of the 7 days it said it should have on the box? Or why isn't this device connecting to my Android phone, or where'd all my steps go? Those were the types of tickets and requests that would make it to my desk. Spent a lot of time thinking about best ways to get to the bottom of these types of problems, which led me to start Memfault. You can find my thoughts about embedded engineering in general on Memfault's blog called Interrupt. If you haven't seen it before, I encourage you to check it out. Personal favorite of mine is how to debug a hard fault. So today, what I would like to talk to you about is just a recap of what it takes to ship a hardware product out there in the field and how the work doesn't stop post-launch, how we can integrate device reliability engineering practices into our workflows to improve the quality of devices in the field and stay ahead of a mountain of support requests or unexpected RMAs, how you can get started with Memfault and the NRF Connect SDK in under 5 minutes. Memfault and Nordic have been working closely together for years now to make this as easy as possible, so excited to share that with you. And then I'm going to talk about key metrics that every company that's building a battery or connected application should be tracking. Shipping on time. What does that actually entail? What does that typically look like? So you're all probably somewhat familiar with this rough timeline here, where we go from a designing phase through prototyping, through different phases in the factory up to ramp and launch. So our engineering validation, our EVT phase, where we might only have a handful of configurations. Once we feel good about kind of the bring up and the peripherals and how the board is wired up, typically move to a DVT phase, a design validation phase, where we start to make sure that all the manufacturing stations are wired up, that sort of the body of the product is starting to look good. And then a production validation phase where sort of optimizing for maximum yield and speed. Then of course, like ramping, it takes time to build thousands or tens of thousands or millions of units depending on your scale, and then launch where the product is available to end customers. Industry standard, if you're doing well these days, all of these phases when it comes to building hardware takes about a year. I'd say increasingly what's taking place is the amount of firmware involved in getting a hardware product to market. And there's a bunch of deliveries along the way. In the first early prototyping phases, you need to do board bring up, make sure all those peripherals are working as they said they should on the data sheet. You need to get manufacturing firmware in place so that the product can be tested on the line. You need to complete the firmware in time for the ship date. And that's where the day zero firmware is what I like to calling it. Making sure you have that complete ahead of launch is really important. What is a day zero firmware? I'm sure many of you are familiar with it, but the concept is you get a firmware in place that basically all it knows how to do is factory reset the device and update to a newer firmware. What this buys you is two main advantages. One, every time someone unboxes the device, they update to the latest firmware that's there. So everyone's always on the latest and greatest, and they don't just stick using whatever you had ready right before launch. And two, it extends the amount of time that you have to work on this final firmware. By not needing to bake it in at the factory, you're effectively buying yourself 4 or more weeks as you ramp up to mass production, where you can get more in place and have things ready to go. Can't emphasize enough how important it is to have a firmware update strategy in place. And it's one of the things first on my checklist when sort of like building out a new product is making sure you have that ready to go, because you want that to be as robust as possible by the time you launch. So congrats, you've gotten the hardware to market. It's launched out in the field. Consumers or customers or other businesses are starting to buy and use your product. Everything is great, right? Well, not so fast. I'm sure for any of you who have shipped hardware before, this is very familiar. Irrespective of the amount of rigor you provide pre-launch, there's always going to be some interesting bugs in the field. Customers have a tendency to use devices in ways that no one would ever envision, and you might need to get to the bottom of that. There's RMA rates that you need to stay on top of. You don't want your return rate to get too high, or you're not going to make any money on your product. There's a constantly evolving ecosystem, irrespective of whatever connectivity you use, whether it's cellular or Bluetooth or Wi-Fi. So there's security patches that you're going to need to make to keep your device safe. There's features that you probably had to cut pre-launch that maybe have been deemed necessary post-launch to get in place. And there's customer reviews and complaints that, especially during the first 6 months of launch, are really important for building the right brand recognition and not scaring people away from buying the product. I still talk to folks today who thinks these things aren't going to happen to you. I have to tell you that they are. I've never seen a company ship a product to market where there aren't some number of issues or defects that they have to work through. Jack Gansel quotes that 10 to 100 defects per 1,000 lines of code is sort of an industry standard that's out there. Some of these issues will be big issues, some won't be so bad, and some, as you have more devices in the field, you'll inevitably encounter problems in production. I like to the quote on the right, I think, is an interesting one that talks about Curiosity landing on Mars. And even with the rigor they applied pre-launch for that rover, they still ran into a number of issues where they wound up firmware updating the device once it was out there in the field. So how do you get ahead and sort of stay ahead of these problems? Well, that's where you can de-risk all of these components with device reliability engineering best practices. Number one, you need a robust firmware OTA system in place. I already kind of touched upon that. Number two, you need a way to understand what types of problems are taking place in the field. That's what we call performance monitoring. This could be things from, was a new iPhone release that's kind of introduced interoperability problems with the Bluetooth stack you're using, or was a new battery rolled in at the factory line and you're starting to see degradation and sort of battery performance that's taking place out there. Is there a new cellular tower that was updated that's now leading to issues being connected? If you don't have performance monitoring in place, you're not going to be able to stay ahead of what issues are taking place in the environment around folks in the field. And then, of course, it's one thing to know there's issues. Now you need the data to actually be able to fix them. And this is where remote debugging comes in. This is the concept of being able to extract error data, log data, core dumps. We'll talk about it a bit in this webinar from the field to figure out what's taking place. All of that encountered, what we like to kind of look at is how our business is doing rolling out device reliability engineering, and this is where we have our device reliability maturity model. Talking to thousands of companies over the last number of years, what I still see in the industry is we're still too reactive. A lot of times companies don't have infrastructure in place to get these insights and understand what's happening. They wait for customers to complain. Once customers complain, in many ways, there's no visibility into what's happening on the device. And so a new firmware has to be rolled out. And in some cases, folks skipped putting a firmware update strategy in their device, and there's no way to even do that. So now people have to go to physical sites or send out new boards to get logs or information about what's taking place. Where companies really need to be and should be is on the right side of this curve, being proactive and strategic about how they prioritize what problems they focus on and fix. And this is where performance monitoring really comes into play, because you can get the exact you can figure out exactly what devices are being impacted by certain problems. Is it 90% of the fleet or is it 0.1% of the fleet? You probably want to fix that 90% of the fleet problem first. So what we're going to spend some time talking about today is how to move from a reactive debugging approach to a proactive debugging approach with Memfault and the NRF Connect SDK. The challenge about sort of deferring getting a system in place is the costs and time compound. So early, in engineering validation, if you have 10 units and there's a problem, it's feasible for someone like myself as an embedded engineer to crack open every unit and look at what's taking place and reproduce the problems and figure out what's going on. But as you go through your design phases, the number of devices and the turnaround time to figure out what's happening takes longer and longer and longer. And once you're out in the field and you're seeing issues, now you're talking about problems where you might have to hold up your factory line for weeks, damaging revenue. You might be getting RMA rates that are too high. If we look at a 1% RMA rate for 100,000 devices that costs a couple $100, we're talking millions of dollars of losses as things pile up. And with device reliability engineering, what you can get in place is a much faster feedback loop. So you save time, money, and resources getting to the bottom of problems and shipping the highest quality product to end customers. So why doesn't everyone build a solution for device reliability engineering? Why isn't more of this in place today? Well, in reality, it's pretty hard. Outside of the firmware world, there's a lot of analysis you have to apply on this data to get the types of insights we're talking about. And that generally requires a full-size cloud team, front-end engineers, back-end engineers, data scientists to extract insights, infrastructure engineers to make sure sort of the site scales and information is up there. The challenge is a lot of this data also requires firmware expertise to understand what's there. We're talking about, generally speaking, code written in C or assembly, unwinding stack traces or kind of recovering insights from a cellular modem or a Bluetooth chip require knowledge of the connectivity stacks that are there and how debug information works at this level, a skill set that's not typical, I would say, of a cloud or software engineer. We also have to keep in mind that monitoring devices is very different from monitoring servers. There's a lot of tools in place that help folks monitor servers, but when it comes to devices, there's a lot of unique challenges. One, just the sheer number of devices far outscales the number of servers that a company would typically monitor. 1,000 servers running a cloud system would be considered a pretty large deployment. In the IoT world, that's a pretty small number of devices. And there's also just unique requirements for devices. Devices don't always know the time. They're generally not connected to the internet all the time or have very intermittent connectivity. Many times they have to travel through many hops to get to the internet, a gateway or a Bluetooth phone or a proxy of sorts. And then the third piece is, we looked at that timeline. We're doing well. It takes us a year to get a product to market. If we wanted to build out a device reliability engineering solution, now we're talking additional NRE in time to have something in place by launch. All of that combined just makes it hard for companies to work into their schedule. And that's where I'm really excited to talk to you about what we've been doing at Memfault with Nordic and the platform that we've put in place out of the box in the NRF Connect SDK. Requires no cloud work on your side. There's basically one K-config option you have to flip to enable Memfault. It's compatible with Nordic's entire chipset portfolio, so all Bluetooth chips, all Wi-Fi chips, and all cellular chips. What we've done with our sort of design and our SDK is all of the information that's collected on the embedded device, we break it up into opaque packets that we call chunks. These chunks just have to be forwarded to an endpoint that can eventually post the data to the Memfault cloud, and then we'll handle all of the reassembly on our side. This allows us to have a protocol agnostic transport that works on mobile apps. It works on AWS IoT or MQTT transports or sort of other proprietary topologies that you may have. And we've designed the SDK itself from the ground up for embedded use case first. So incredibly small code footprint as well as RAM footprint, binary serialization protocols, which we'll talk a bit about later, to keep the storage on the device as well as transport overhead as small as possible. And inside the NRF Connect SDK, you can find extensive documentation about Memfault and how it works, as well as examples of how to send data to pretty much all setups. So through an iOS application, through an Android application, as well as through the cloud. It's one thing to collect the data. It's another thing to turn it into insights. I won't go into great detail here, but I just wanted to give you a quick overview of what we're doing once the data hits the Memfault cloud. We're taking all of the chunks that are coming in, we're reassembling them and deserializing them into data types. So what you see in the deserializer phase here, so the second stage of the pipeline, is recovering information like, hey, we detected a crash, core dump information, as well as heartbeats, which are metrics, aggregated metrics for what was happening on the system. We take that binary data and then we restitch it on our side to recover meaningful information. So in the case of a crash, we'll be able to recover the exact call stack that was in place when the system reset. When we're talking about metrics, we'll recover the names of metrics, human readable names of metrics, so you can see what's there. We pipe all of that data into our deduplication engine, where we cluster like problems together so that we can tell you, hey, 90% of the fleet is suffering one problem, and this other problem, it only accounts for 0.2% of the fleet. And then finally, all of that data is indexed and aggregated along a few dimensions. Notably, we aggregate all of the data by software version and by time, so you can kind of look at over time or by software version what is taking place. And then we index the data fleet-wide as well as per device. What this lets you do is look at high-level trends, so you can say, oh, it looks like on the latest release, battery life has regressed. And then you can drill into individual devices and figure out exactly what was happening on devices experiencing bad battery life so you can fix the problem. And then, of course, there's a web interface and alerts that you can use to be proactive about how diving into these issues. Something else that's really cool with the Memfault and NRF Connect SDK is we've worked with the engineering team at Nordic to integrate metrics outside of the box that you would want to have in place to understand how your device is performing. And we'll talk about a few of them later. In this screenshot, one of the ones that's highlighted is just the time it takes to open an LTE connection. A really good indicator of kind of how the device is performing, and if they're sort of like in an environment that isn't very good. So I want to briefly talk about how you can get started with the Memfault and NRF Connect SDK today. Because we're pre-integrated inside the SDK itself, it's super, super easy. First step is you just need to register and create a Memfault project. We have a link down here. Because of our partnership with Nordic, you can try up to 100 devices during development for free forever. And you can create a project where we'll give you exact instructions of how to add it to your system. I'm actually going to break out to a live demo right now and walk you through that. Let's break out to a screen. So if we follow the link here, I've already created a Memfault account, so I don't have to enter my name and sign up again. But when I click the link, it takes me to a sort of pre-setup for the NRF Connect SDK. I can just hit create project here, and we'll get a detailed guide of exactly what steps need to take place to wire things up. When it comes to the NRF Connect SDK, as I mentioned earlier, it's really just one kconfig option to flip it on, and one project key that you have to add to the system. Project key is how data is routed to the correct project in Memfault. Let me just go to the kind of next setup here. Inside the NRF Connect SDK, dating back all the way to NCS 1.6, I hope you're all using something newer by now, is demo apps as well, where you can just try out Memfault. So what we're going to look at right now is the debug Memfault demo app, which can flash onto 9160 DK and take a look at what's there. So what we'll do is we'll go to the terminal here where I've already downloaded the SDK itself. We'll just insert the project key and we'll compile the system. And that shouldn't take very long at all. Kind of just let it run through, wire up. What we're going to do next after this finishes building is we're going to upload the symbol file generated to Memfault. This is what Memfault uses as a mapping file to go from binary data formats, so that we keep the on-device footprint super small, to human readable formats in the Memfault cloud. And so we'll just upload that symbol file. We will flash the board using West. I imagine most of you are familiar with that. So we see the board flashing. And then on this terminal over here, I've already started a console. The way the example app works is you can hit the buttons and it will sort of reset the device and put it through different modes. So let's hit one of the buttons. We see the Zephyr fault handler is invoked. When the device reboots and it connects to the network, it will send up to Memfault information about this stack trace that took place. And so like, if we're looking at it here, we basically just see addresses, but on the Memfault side, we'll get a richer sort of decoded format of what was actually there. So this is the example project. The data has already arrived a second ago. If we dig into this fault and open it up, what we'll see is the exact kind of state of the system, as I mentioned, leading up to the crash. So we know that, well, I clicked a button in the button handler on line 66. That's where the crash took place. I won't go through all of it now, but you'll get register information as you walk through the different frames about what's wired up. You can also look at system state. So if there's important state machines or global variables you want to collect, you get that as well. There's information for all of the tasks that we're running on the system. This can be super helpful for digging into deadlocks. Basically, if you've used VS Code or GDB at your desk, what we do with Memfault is we give you that same degree of information, but from devices that aren't connected halfway across the world. What you also get out of the box is pre-canned metrics about what is happening on the system. So if we wanted to look at LTE state or things like that, we can flip that on. In this case, there's only been two events that have taken place over time. This can be more interesting to look at, but we can see, oh, this connection only took 7 seconds. That's actually pretty good. And that's all there is. That's all there is to it. 5 minutes, 5 minutes or less, like I said. I encourage you to check it out. As I mentioned, I showed you the CLI tool for uploading symbol files. It can also be done via the UI. This is just a screenshot showing the same information that we just looked at live. Of course, your system is going to have its own application and usage and things happening as well. And so one of the things we've really spent a lot of time on with our SDK is making it super extensible. So with 2 lines of code, you can define any metrics that you want. So say, for example, you're using MQTT. You could very easily define a new metric that tracks how many bytes of MQTT data you're sending. And then you would just have to update that value every time in the driver that it's taking place. And so folks will use this to track application-specific information. We'll talk a little bit more about how this can be applied to debug battery life problems later in the webinar. How do metrics work? Kind of wanted to highlight this a little bit because I think it's different than what I see as a first approach from a lot of folks. One of the things that we do with metrics, which we call heartbeat metrics, is we pre-aggregate the data on the device over an interval. Interval we typically recommend is 1 hour. And then what you wind up getting is a snapshot over that hour of what was transpiring on the system. So things like how much time was spent running different tasks, how much time did we spend trying to connect to LTE, how many times did we switch between towers, or did the network disconnect. At the end of the hour, we basically grab a snapshot of that aggregation and save it up for sending. What this lets us do is it's a super efficient way for batching a bunch of data on the device if there isn't a connection available. It also minimizes the amount of data that you have to send. I've seen a lot of approaches where folks will just send data once a minute or once every 10 seconds. I highly recommend not doing that because you'll blow through most data budgets and really hurt your battery life doing so, which is why we have this heartbeat approach. We have a bunch of content about it in general. I linked here. You can also find a webinar about it on our website. Format-wise, what we've done is we've created a binary serialization protocol that leverages CBOR, where we can take sort of the human-readable set of metrics, the JSON you see there on your left, and pack it in a really efficient format. And so you can see here, if we were just sending this information in JSON, it would be over 450 bytes. If we're sending it with Memfault, it actually winds up being a little bit smaller than packing the data in a C structure because we're using a variable encoding scheme for integers. What this lets us do is it minimizes the RAM overhead on the device needed to store it while we're waiting for it to be sent. It minimizes the amount of CPU that's needed to encode. For bandwidth intensive applications, where you don't have a big data budget, it keeps the footprint super small. Also by, all of those factors reduces power consumption. So when it comes to reliability metrics, I wanted to talk about table stakes and some of the things that every single company should have in place or be able to answer right off the bat. And one of them is, the first and most important is crashiness. You need to understand what types of resets are happening on your devices in the field. And there's many different types of bugs embedded that can lead to crashes. Worked with a lot of customers who have tried to get to the bottom of really strange hardware watchdogs. Underlying cause winds up being deadlocks or race conditions in the stack. There's bugs that sometimes only manifest when certain silicon is on the device. So when there's maybe there's a oscillator that kind of isn't exactly what it should be, or a diode that peak power draw is a little bit worse than it was on the data sheet. You need to figure out, are those types of crashes taking place where you need to improve your quality in the factory line itself. Power regressions, resource exhaustion is really common. So out of memory type issues, stack overflows, performance considerations, especially for folks who are doing something that's algorithmic, can wind up eating a lot of the compute and causing other parts of the system to stall. And then some good old favorites of memory corruption, interoperability between connectivity stacks, a lot of reasons that can cause bugs. One of the things to get a benchmark, and something that we collect out of the box in the Memfault and NRF Connect SDK, is how often is this taking place? And the way we recommend tracking this is a metric we call crash-free hours. It looks at the amount of hours that a device has been up and operating where it hasn't reset, and it compares it against the number of hours where a reset took place. The reason we recommend tracking it this way is it's super low latency. Basically, the devices, as soon as you deploy your release out in the field, you can start to get a sense of what this metric is looking like. If you're tracking something like uptime, you have to wait a long time before there's sort of data about is it better or worse, if that's how things are being compared. And so for being proactive, we really recommend tracking this type of information in a way where once you start to average or aggregate the data in the field, you know right away if it's better or worse. We also index it by software version so that when you ship a new release or you do a new spin from the factory on the device, you can tell, hey, is this definitively better or is it worse? And you can compare it over time to see if any new problems were introduced. In Memfault itself, what we'll then do is show you which issues and problems are most prevalent to guide prioritization. So you can look and see exactly how many times an issue has occurred by a particular software version and the number of devices that have been impacted. And what we recommend doing is, working through the list of problems to fix the issues that are the highest impact, affect the most folks in the fleet. Fixing crashes themselves, just getting logs often isn't enough. That just gives you one frame, basically the function where things went wrong, but often you need a lot more supporting context. What was the call stack leading into the frame? What was the state of particular, the Bluetooth state machine, or the state of kind of other threads while things were running? And that's where the core dump strategy and approach that you get out of the box helps out. We're wired up into the fault handlers in the NRF Connect SDK and Zephyr. So out of the box, you'll just get all of this information, precise sort of point-in-time snapshot of what's happening on the system. A huge percentage of IoT devices wind up being battery powered for some point in time. And so what I wanted to talk about now is the metrics that you must collect to get to the bottom of battery life issues and even understand how is battery life looking in the field at large. critically important to customers with battery-powered products is that it hits the life expectancy that's promised. If it's out of power, it's a non-functional device. Some devices don't even have a rechargeable battery, and so you need to get the lifetime that was there. It's a problem that feels near and dear to me because I spent a lot of time focusing on it when I worked at Pebble. At Pebble, we promised on our 130 milliamp hour battery that a customer would get 7 days of battery life when they fully charged it. And then we actually wound up shipping a even smaller watch with a 56 milliamp hour battery where we promised 2 days of battery life. It was a key differentiator. It was also the number one or two support requests we would get from customers is why their battery life didn't hit those goals, because it was something our audience cared a lot about. And we spent man years of engineering time trying to figure out best ways to look at this and view it. If any of you have worked with batteries before, you know it's a harder problem than it seems on the surface. Batteries, typically lithium-ion batteries, have a non-linear discharge curve. There's a point in time where it's somewhat linear, but as you kind of get to the bottom and it really drops off, this can make it really hard to measure percentages accurately. Internal resistance, so basically all batteries have internal resistance as well. This means that when there's a high power draw, you can sometimes get inaccurate readings. So for example, when I worked on the Pebble smartwatches, we had a vibration motor. Whenever that was running, it would droop the rail we were sampling to extrapolate battery percentage, and it would drive an inaccurate result. Batteries degrade over time. They are temperature sensitive, and there can be wide variation between different suppliers when it comes to batteries as well. So what do you do? Well, one of the things when it comes to battery life metrics is you really have to think through how you're going to collect this information. The first approach I see from a lot of folks is just to collect the battery percentage at a fixed interval in time. So every 15 minutes, I'll send up what the current battery state is. This winds up being tricky because it sometimes hides information. So for example, in this diagram here, if we had like a big power bug and then someone charged the system and we only sampled between the 80% and 70%, we never see the drop off that was here. So we need a little bit more information. For example, why is it charging? The other pain point is when it comes to wanting to understand battery life, now you need to wait for the devices to fully discharge before you have a sense of what the battery life on the system was. And this is sort of just a diagram of exactly what I'm talking about, but if we're trying to compute the battery life expectancy and we have some devices that are going through being charged at different intervals, some devices where there's like power bugs that are in place, it can be very difficult to take this information and figure out what's the actual battery life, typical battery life that we're seeing in the field. This is where we recommend tracking the battery drop per hour. So for every hour where the device is not charging, collect the percent drop of battery on the device and report that up as a metric. What that makes it really easy to do across your fleet is aggregate all of this information and get a sense of what the projected hours of battery life for your product is. You basically take the average of all of these drops, you divide it by 100, and that gives you sort of the number of days that are there. It also makes it really easy to search for devices that are experiencing unexpected battery drains, because you can start to look for example, show me all of the devices where there was a drop beyond 15%, for example. So here's a chart within Memfault demonstrating charge level drop where we're plotting over time two different software releases. Our 1.0.0 release, that's in blue, and our 1.1.0 release, which is in red. And what we can see is that it's almost 2x worse than the previous version. So we know there's a bug in place that we have to drill into and get to the bottom of. So how do you figure out the root cause of these power regressions? In production, it's not an easy task. The first line of defense is making sure you have the battery tracking drop metric in place, like I just mentioned. And then the next layer is sort of determining every system winds up having some subset of subsystems that are power hungry. So things like the CPU running, if you're using GPS, things like trying to get a GNSS fix, running cellular, these are all reasons that are there. And what you can do with Memfault with those 2 lines of code is you can easily instrument these subsystems. So you can start to add tracking around how often was the display on, how long did it take me to connect to a satellite network, information like that. And then you can very easily look from release to release to see if those subsystems are seeing more draw. So in the examples on the right, we were looking at a backlight, and we can see it kind of went up. It was on way more between 2 releases. And we're also looking at CPU sleep time. We can see that went down, which tells me that the CPU is running more than it was sleeping. So those are areas you need to focus in and dig into. All right, so we talked about battery monitoring. What I want to talk a little bit about is the key metrics you need in place to start to assess, what the quality of the connectivity that you have. To some degree, it doesn't matter what connectivity transport you're using. They all have the same key sets of information that you want to extract. In a moment, we'll specifically focus on cellular. But to start, I just wanted to talk about high level, the key pieces you want in place if you're using Bluetooth or you're using cellular or Wi-Fi. Things like signal strength, things like the radio channel that you're on. Often if devices get pinned on a certain channel where there's a lot of noise, you'll see more disconnects, for example. You want to know the total number of times that connection attempts have been made or disconnects have happened. You want number of times that failures have taken place, so you can get a sense of, are there devices out there that are just in a constant reconnect loop. And generally, especially when we're talking about bandwidth and power, you want to keep track of how much data are we sending and receiving, because that's when we're talking about wireless technologies, that's sort of a big driver of battery drain. Inside the NRF Connect SDK out of the box, we have these defined for Bluetooth and for cellular LTE-M. So this is just an example of the names of the metrics when we're talking about NRF 91 usage. We'll track the time it takes to connect. We'll track the amount of connections losses that have taken place, so how often is the signal dropping. We'll talk about how long has the device been connected, and the amount of data that is sent. And then on the right there, you can see we can look in Memfault to see how that's trending over time. Once you have these metrics in place, you can also start to look for outliers in your fleet. You can figure out if the top 10% of, or the worst 10% of devices experience X amount of connection losses in an hour. You can start to search for that and drill into devices where that was experienced. So this is the device search view within Memfault, where we're looking over historical data and we're identifying devices that have kind of had a high number of disconnects, and one pops up. And this is where indexing the data on the device level can be really, really helpful, because you can start to pull up a point in time within Memfault and look at the exact state of the system. With Nordic, we've also worked in some pretty advanced capture modes to get even more information about what's happening on the device. This is one that I think is super cool. It's maybe some of you have used the modem trace capture at your desk. This gives you information about the exact packets that are being sent between the tower and the modem on the NRF 91 at a point in time. With the NRF Connect SDK, what you can do is scoop these up remotely. We've tuned it to sort of minimize the amount of data that has to be transferred and get sort of the exact AT commands, LT, RRC commands being sent from the device at that point in time. So if we were searching for devices experiencing a large number of disconnects and they'd sent up one of these, we could then kind of go through and see, why did the tower reject it? What was the problems that were actually taking place and what was there? There's an example of this in the NRF Connect SDK as well. Last part I wanted to touch on was what I call critical post-release metrics. These are the metrics. Every company needs 3 or 4 metrics that you're looking at every single release to understand, is the fleet better or worse than it was before. If you're a battery powered product, battery has to be one of them. I always recommend looking at it in 2 different ways. Mean percent of battery drop per hour. So what is that average drop we're looking at? And then if we're presenting it in days, so we're taking that 100 and dividing it, what's the number of days that are there? The average time you're connected to your transport, is that going up or down? That will give you a signal of if you introduced improvements or regressions in terms of what your connectivity looks like. And then the third piece is just generally like usage of other peripherals or parts of the system that might be high power draw. So in this case, average GNS at fixed time, has that gone up and down? And what you can look at between releases is where things are trending. Hopefully they're always trending better, but by tracking information at an hourly interval, it's super low latency. You get it out there in the field. You can start to look at the data. If the numbers are trending in a negative direction, you can roll back the firmware release or debug what's there and get a new update out there to fix it. But if you don't have something like this in place today, this is kind of the crux of device reliability engineering, and being proactive is getting this information from the start. Thanks for joining the talk today. I hope you all enjoyed it. Just wanted to share a few final links to wrap up. We'll share the deck after as well. First one is memfault.io/demo. That's access to an interactive demo of the Memfault tool if you want to play around yourself before you even sign up or do an integration. Really easy to kind of check out the tool from there. Just re-including the links of how to get started with Memfault and the NRF Connect SDK today. Sign up link for our service, as well as the docs. And the final link is how to join the interrupt community. A lot of great discussion about embedded best practices, Memfault, etc. in there. So I encourage you to check it out. If you'd like to reach out to me personally, please find me on LinkedIn and say hi. I'm always happy to chat about a good bug or embedded development in general.
Thanks, Chris. Very informative presentation. I really liked it. And we're ready to take questions. If you haven't asked already, you feel free to ask it. We already have some questions already. We can go through them. Okay, so first one is, how much impact does Memfault have on device battery life?
Can you hear me? Sound good?
Super.
Awesome. Thanks, Ali. And good question. Memfault has a negligible impact on the battery life. The crash information that I showed you, there's nothing that's even running until a fault occurs. So if you get your firmware to be crash-free, there's no overhead at all. And then all of the metric systems that we put together, we designed those from the ground up for embedded use cases first. So we're not sending megs of JSON. We're aggregating data on device in that heartbeat format I mentioned. And in fact, most of our customers use the system to save their battery life, reduce the overall draw on the system.
Great. I think we can move to the next question then. So the next question is, what happens on devices with intermittent connectivity? Does Memfault still work?
I like to say all we need is an eventual connection to the internet. So whether you're using a Nordic Bluetooth device or Wi-Fi device or using cellular and proxying the data through your own cloud, it just has to eventually be posted to Memfault. One of the things we did, and I mentioned in the webinar with our SDK, is all the information we collect is broken up into opaque packets we call chunks. And these just need to be forwarded through whatever your transport is. So it makes it super easy to pipe the data through and not have to worry about reassembling or restitching stuff beyond the MTU on your side. We do that all on our side.
Absolutely. And I think there are apps as well, like there's a gateway app for Bluetooth Low Energy, NRF Memfault or something that you can use as a gateway for Bluetooth solution.
Yes, exactly. It's actually right in the Nordic GitHub project, sort of alongside SDK NRF. There's an iOS and Android example for proxying through mobile phones if you're using Bluetooth.
Thanks, Chris. Let's take the other one. Okay, so how much space does Memfault require on a device?
Yeah, so typical configuration of Memfault requires 4.5K of ROM and a K.5 of RAM. We fit down into, as small as like 32K footprints, and it's very configurable as well. So if you're really maxed out and you have no space for it, you can dial it down even farther from there.
Interesting. Okay, then. Am I able to send data to my own cloud first and then to Memfault, or does data have to go direct to Memfault?
Data does not have to go directly through Memfault. If you're sort of already sending data to your own cloud, you can very easily pipe the Memfault chunks, send it to your cloud, and then just call a REST API from our side. So we see a lot of folks do that when they're working with working with MQTT or some NB-IoT setup or other things where they're piping data to their own system.
That's interesting. So you also have cloud-to-cloud kind of like APIs that allows people to get the data to their own cloud and then propagate it to Memfault.
Yeah, and there's actually examples of that in some of the demo apps I mentioned inside the NRF Connect SDK. So inside the asset tracker application, for example, there's an example of how to pipe Memfault data through MQTT.
Interesting. Okay, and then we have the last question. It's not quite related to the topic, but I noticed that you are working on a Mac. Are you using a VM or working natively?
It's a fun one. Well, I'm working natively. One of my goals when I'm doing development is getting my iteration cycle as fast as possible, so I can sort of reflash my board, see what's happening, and I always find once you add a VM in the mix, you're copying and pasting between two different environments, or
That's true.
Kind of like having it runs a little bit slower. And so one of the things that's really nice about the NRF Connect SDK and Zephyr is it's very cross-platform. So it's quite simple to run in whatever environment you prefer, though. I'm a bit of a Mac champion.
Absolutely. I think that was the last question. And so thank you, everyone. Thank you, Chris, for the great presentation, and thank you everyone for joining.
Yeah, thanks everyone for joining today. And like I said at the end, don't hesitate to reach out if you have a good bug you want to talk about or share an embedded story. I always love to hear them.
Absolutely. I mean, I love the Interrupt blog. It's quite rich with really useful information, and it's very interesting to read. All right. So thank you, everyone. Bye-bye.
Have a good one.